Okay, let's get started today. Our last Monday together, and the test is on Wednesday, of course. So this is a bad day for people to be missing. The weather's not that bad, okay? So I hope they're going to watch the tape, because otherwise they're not going to be prepared for this test number 3, which is coming up on Wednesday, of course. There is one more review session for that test, which will be right after class, the usual review session. The answers to the test review are posted. So I sent an email about that. I don't think there's an announcement about that. But the answers are posted on the Blackboard page under the sample tests link. As far as the test goes on Wednesday, I made a slight adjustment for you. So this second integration homework, which we're going to talk about today, okay, is going to be not due until the time of the final. So that will be covered on the final exam, okay? So that problems on that homework will be on the final exam, but not on test number 3. Everyone hear that, okay? So this integration homework part 2 due on May the 11th at the time of the final. But the part 1 is still due on Wednesday, and questions like questions from part 1 will still be on the test number 3, okay? So I just relaxed the schedule a little bit because I want to make sure that you're done with your homework that's due tonight, this homework 4.4, and this part 1, which is due at the time of the test. It's not due at midnight, but it's due at the time of the test because I want you ready for that for the test, okay? So everyone got that? So the problems on the test review that are like the part 2 homework, those are problems 9 and 10, the last 2 problems from the test review, okay? That's where we're doing integration, finding area under curve with pencil and paper, analytically, where we can find the area under the curve exactly, and that's what we're going to talk about today, okay? So in part 1, that's where you're using, sometimes you can find the area under the curve exactly if the shape is just a nice geometric shape, or this is using the rectangles, right, to filling up the area with rectangles in order to approximate the area under the curve. That will be still on test number 3, okay? That will still be on test number 3, all right? Okay, so finish that part 1, and then part 2 you have another week, so don't forget about it because it's still due, but not due until the following Wednesday, okay, at the time of the final exam. Here are some notes about the final exam. So you've got to worry about test number 3 first, okay? So, but there will be some review sessions for the final exam. So this is for the final exam. It'll either be with Fernando or John. Fernando is the supplemental instructor for the other Math 1306 that uses the same book as we do, that meets at 8:30. Right before this class. So there'll be a review session on Friday, this Friday, May the 6th, from 10 to noon, and then on Monday, May the 9th, from 10 to noon, okay? So you've got two chances to go to review session there and prepare for the final exam. So we don't have a review for the final exam like the reviews for the midterm tests, okay? You are to study your previous notes, your homework, your sample test, and your test. I'm going to be making up problems like problems on the previous tests and the sample tests, okay? So you know what to expect, but you don't have a blank final exam review to work on, okay? But you still have a final exam you still have a review for test number 3, so be sure you work on that along with that those 2 homeworks that are due by Wednesday for the test on Wednesday. Okay, and then the final exam is on May the 11th. All right. Now I'm getting a lot of questions about the class currency. It's mostly up to date, except I haven't added points for the last couple of weeks of the SI session. So if you went to see John in the past couple of weeks, those points may not be added. If you want to turn in your receipt for your course evaluation, remember that is worth $5, okay? So you can turn that in to me today, or you can turn that in Wednesday. Wednesday will be the last day, though, so you have to turn it in at the time of the test. And then remember, you've got that class activity 4 that I passed out last time. John's got some extra copies of that. You can, if you don't have your copy, you can get a copy of that from John. Now, to help you with that, that class activity, I made this video yesterday because we're not going to talk about that class activity is about integration, but it's an application of integration called density functions, which are important in probability and statistics, and we're not going to have time to talk about that in class. So I made a video of that yesterday of what I was going to talk about in class about density functions. And so that link to that video, it's a YouTube video just like the other class lecture videos. So you can get to that video by following this link, right? Okay, and that will explain a little bit about density functions. And then also at the very end of the video, maybe the last 10 minutes or so, it will it'll give you a little hints there on how to do the class activity 4. So I actually get you started on the first problem in that class activity. Okay, and to help you with those class activities, you're going to have to use Desmos, and there are links to the Desmos tools that you want to use for problem 1 and for problem 2 right here. Also in the class announcement. So when you're working on class activity 4, don't forget that. When you're working on problem 1, here's the Desmos. Here's the link to the Desmos tool to help you with that problem number 1. And when you're working on problem 2, here's the link to the Desmos tool to help you with that problem number 2. So if you have any questions about class activity 4, I think John can help you, or you can come by my office and ask me, and we can look at it together. I don't think the Math Center in North 925 is going to be very helpful. They're probably not going to know what you're talking about when if you ask them to help you with this class activity. So I think it'll be either John or myself if you need some help with that. So remember, that's extra credit. Also, that's worth an additional $5 of extra credit. Today is the last day that we're signing roll. So in a second here, John will pass out the roll, okay? So you have to be here Wednesday, of course, because that's the test. So I'm not taking roll on Wednesday. So remember, if you have not violated the attendance policy, that's worth $15, okay, added to your class currency. So since Monday is the last final, the week from today, is the last last SI session. That's the last day you can earn points for going to the SI session is on Monday. So I will on Monday update the extra credit currency, okay, and that will also include extra credit for what happens on test number 3, okay, will be included in that, okay, and I think that would essentially be complete on Monday. So what you need to bring to me at the time of the final, or you can email it to me prior to the final exam, is what John is going to pass out right now. Let me see that sheet there. Okay, and this is the shopping cart for how you want to expend your calculus currency. Okay, so what you need to do is fill out this sheet, okay, for me, and then bring that with you to the time of the final exam, or send it to me prior to the final exam, okay? But you may want to wait until you get all the currency in the grade book, which will be again a week from today on Monday. So if you're gonna buy out of the final exam, remember that takes $60. You obviously won't show up for the final exam, so you'll have to send this to me by email, right? Okay, so I can have a record of that. Otherwise, I'm going to wonder what happened to you on the day of the final exam, right? Okay, so John is going to pass that out now. You can pass that out, John, for us? Okay, all right. So John's going to pass this out now. Don't lose it, because you want to bring it to you at the time of the final exam, but you can be thinking about now, between now and the final exam, how you want to expend your currency, right? Okay. Yeah.
With our currency for our homework and quizzes, is that going to be in on Monday, or is it already?
That should be in on Monday. The only assignment left that would be due would be the integration part 2, okay? But I think I'll have enough information at that time to know if you're going to get bonus points for the homework, right? Because you get, how much is it there? Yeah, it's a certain number of dollars if your average is above 80, a certain number of dollars if your average is above 90, right? Okay? And I promised to bump that up a little bit because we folded the quizzes into the homework, okay?
By Monday, you're also including attendance.
Yeah, attendance I'll know because today's the last day we're taking attendance.
So on the whole thing.
Yeah, the whole thing should be up to date by then, okay? Right, so take a look at it on Monday. And then but be thinking about it in the meantime. You'll have a rough idea of where you're at in the meantime. Be looking at it and planning on how you want to expend that, okay? So remember, it takes $60 to buy out of the final, so some people will be able to do that, especially once the attendance goes in, okay? Remember, if you choose to buy out of the final, it'll be the average of your 3 midterm tests will count as your final exam grade, okay? So think carefully about that if you want that to happen, all right? The average of your 3 midterm tests will count as your final exam grade. Or if you want to spend $25 and use the final exam score to replace your lowest test score, that frequently is very beneficial, okay? Or if you want to drop homeworks or add points to your midterm scores. You can do a mixture here, all right, as well, okay? Just make sure you don't spend more currency than you have available to you, all right? Because I'm not sure what I'm going to do in that case. That'll confuse me, all right? So I'll have to make some decision if you go over your currency, all right? So some people are asking me, is the currency up to date? Again, I haven't factored in the last couple of weeks of attending the SI sessions. So you may be missing some dollars there, okay? I haven't put in for the turning in the evaluation because that is not due until Wednesday. Remember, however, your currency, remember you get dollars detracted if you score below 70 or below 60 on your midterm tests. So you need to remember that, right? So if you're thinking, my currency hasn't changed recently and I have been going to SI sessions, it may be because dollars got subtracted for test number 2, for instance, right? Okay.
So that survey is for the SI. You can fill it out and turn it in the class, or you can fill it out and turn it in at South 405 at the front desk. There'll be a little box.
Yeah, I'm afraid you don't get currency for that. I didn't have that factored in. Okay. All right. But you do get currency for completing your course evaluations, right? Okay. So that's an easy way to score $5 if you need $5. All right. So you should be aiming for, I think, trying to get at least 25, right? Because $25 will let you replace your lowest midterm with your final exam score, And that can be quite beneficial, okay? That can be quite beneficial. So you should get easy 15 for not violating the attendance policy. If you turn in your evaluation, that'll give you 5. If you do class activity 4, that final extra credit about density functions that I just talked about, the video being posted on the announcements there, that's an extra 5. So so that would give you 25 right there, okay, that you could use to replace your low midterm score with your final exam score, okay? Some of you are going to have the 60, and you may want to buy out of the final exam. So if that's the case, again, send me that prior to the final exam, right? Okay?
So we'll know our test grade prior.
Oh, yeah, you'll know your test 3 grade, and I won't be able to, well, you can come by my office and pick up test number 3, but I will post the answers at least, okay, for you to see. That'll be quickly after the test. I'm not sure how long it'll take me to get the test graded, okay? All right, excellent. Let's look at a couple of problems on the sample test, okay? So here's a copy of the sample test. So again, if you haven't done the test review, be sure that you do that in addition to finishing your homeworks by Wednesday. This is always very helpful, right, okay, in preparing for the test. So you can go to John today at 11:30 and do some more problems here from the test review, okay? And we're just going to do a couple here. Let's look at 1B, and these are just problems to find the rate of change or the derivative function. So these are applying either probably the chain rule or the product rule to find a rate of change function for a particular function. All right. So I'm looking at B now, where we have a square root. And remember, if that shows up on test number 3, the first thing you're going to want to do, right, is rewrite that square root as a fractional exponent, okay? So don't forget that. There's not much we can do with square roots in calculus. We have to convert those to fractional exponents. And you know how to convert square root to a fractional exponent. It means 1/2 power, okay? And then when you've got it written with the 1/2 power right then, you have a lot of practice now in applying the power rule, so it's fairly easy now to find the rate of change, correct? Because you're going to bring the 1/2 down as a coefficient in front, and then subtract 1 from the exponent, right? Okay? But here's where you've got to be careful now, okay? It's not just this simple, because this expression that we're raising to a power is not just plain old x. It's 5 minus 3x, right? It's a little bit more complicated expression that we're raising to a power, so you need to multiply in by the rate of change of that expression, right? So you have to finish this off by multiplying in by the rate of change of 5 minus 3x. That's called the chain rule. So if this is just x to the 1/2 power, finding the rate of change of x to the 1/2 power would be easy. You wouldn't have to go past this step, right? But because it's a little bit more complicated expression than x, you have to multiply in by the rate of change of 5 minus 3x. And of course, what is the rate of change of 5 minus 3x? What? -3, right, yeah. Not 3, but -3, okay? So you don't want to make a sign mistake there, right? The rate of change of 5 minus 3x is going to be -3. And so really that's it. That is the rate of change formula right at that step. Now we can simplify this a little bit because we can multiply, for instance, the -3 times the 1/2. So that would give us -3/2. And then we can take the 5 minus 3x and simplify that a little bit, because 1/2 minus 1 is -1/2. And remember, then we can move that to the denominator to make that a positive 1/2. So we would have -3/2 times 1 over 5 minus 3x to the positive 1/2 power. And then we can rewrite that positive 1/2 power back as a square root, right? because we know when we raise a quantity to the 1/2 power, that means we take the square root of it. So ultimately here, you could simplify this down to minus 3 over 2 times the square root of 5 minus 3x. And that's what I've got written on the answer sheet, okay? But from this point on, all of this is just algebraic simplification. This really is the rate of change formula, okay? There's the rate of change formula, and all we're doing here in the next few steps is just, trying to make that look a little bit prettier, okay? This is a little bit of a clumsy expression. Here it's a little bit easier to work with if it's minus 3 over 2 times the square root of 5 minus 3x. But you've definitely got to get to this step, right? Okay? You've definitely got to get to this step. That's the important step. Huh? Yeah, I think in the book they've been accepting that as essentially complete, right? Okay? In the homework. So I'll probably accept it as full credit there, okay? It would be nice if you simplified, right? Okay? But you definitely want to get right there. Let's take a look at another one here, F, okay? So here we have a combination of both the product rule and, as you'll see here in a second, the chain rule, okay? So this is very clearly, in finding the rate of change of this function g, you're going to use the product rule, right? Because this is a product, correct, of this expression, 5x, and this expression, e to the 3x power, right? So on your index card, which you are allowed to use on Wednesday and on the final exam, be sure that you have the product rule, or at least an example of the product rule written down, right? So you can remember it. So what does the product rule say? It says, okay, if I've got an expression that's the product of two simpler expressions to find its rate of change, I'll take the rate of change of the first factor, which is the 5x here, and what's the rate of change of 5x? That's just plain 5, right? And then I'll just multiply it by the second factor and just leave the second factor as it is. And then add on to that the first factor, which is 5x, times the rate of change of the second factor. So I have to find the rate of change now of e to the 3x. Well, that's an exponential expression, right? So you know that when you find the rate of change of an exponential expression, you just repeat the power, right? So we're going to get e to the 3x again. But again, here's where you have to be careful because the chain rule is going to come into play. If this were just e to the x power, you would be done, okay? The rate of change of e to the x is e to the x. But that exponent is a little bit more complicated now. It's 3x. So when you take the rate of change of e to the 3x power, you do repeat the e to the 3x, but then you have to multiply by the rate of change of 3x, which is what? 3, right, okay? And so to finish that off, you have one final factor there of 3. So we have 5 times e to the 3x plus, I'm going to multiply the 3 times the 15 there, because that's easy to do. And so there is our final rate of change formula, okay? 5 times e to the 3x plus 15x times e to the 3x. Because when you find the rate of change of e to a power, Balkis, all right, e to a power, when you find the rate of change of e to a power, you repeat the e to the power, right? Okay? But then you have to multiply by the rate of change of the power, always, okay? If that were just x, if that were just e to the x, the rate of change of x is just 1. So it wouldn't make any difference. But here it's 3x and the rate of change is 3. So you're multiplying by 3 there, okay? So I think in every one of these examples so this is why it's good to do the sample test, okay, prior to taking the test, because in every one of these examples you're going to have to apply the chain rule at some point, okay? So, or the product rule, but the chain rule especially, right? Okay. So I'm not going to do all these examples because we don't have time for that. But if you look at the g there, right, okay, there you've got 1 over 3x plus 5 squared, right? So the first thing you're going to do is rewrite that as 3x plus 5 to the minus 2 power. You don't want to leave that 3x plus 5 in the denominator. That's going to complicate your life, okay? So write it as 3x plus 5 to the minus 2 power, okay? And then you can just apply the power rule, you see, to find the rate of change of this function. So let's see, s prime of x would be bring the minus 2 down, right? So you have minus 2 times 3x plus 5 to the minus 2 minus 1. So remember, you're subtracting 1 there. So that's going to give you minus 3. But then, what do you have to do? Multiply in by the rate of change of 3x plus 5. Because that's not just x to the minus 2 power. That's 3x plus 5 to the minus 2 power. So you have a little bit more complicated expression to a power. So you have to multiply by the rate of change of that little more complicated expression, which again is just 3, right? Okay, the rate of change of 3x plus 5 is just 3. So you have to finish this off by multiplying by 3. This was a negative 2 power. So I subtracted 1 from it, and it gave me minus 3, right? Okay, remember that's just the power rule. You brought the minus 2 down, okay, and then you subtracted 1 from the exponent, okay? So that is just the plain power rule. When we multiply in by the 3, that is the chain rule. Okay? All right. And then you can simplify this expression a little bit. Ultimately, this would come out, if you tried simplifying this expression, as minus 6 over 3x plus 5 cubed. Because you can multiply the minus 2 times the 3. That's going to give you minus 6. And then that minus 3, well, you know you can get rid of that negative exponent by inverting, right? So you can bring that 3x plus 5 to the minus 3 power back down into the denominator and change that minus 3 to positive 3. So there would be a simplified version of the rate of change formula. Okay? All right, so lots more examples there on the test review, okay? So of using I think either the chain rule or the product rule. So make sure that you look at those prior to, and practice those prior to the test on Wednesday. You can start right after class with John, okay? Working on that. All right, let's look at another one here. I want to look at 2b, okay? 2b. So here we've got a function, and we're just going to, which is h, which is x cubed minus 5x squared plus 8x. And in this case, we don't have to find the rate of change or the second rate of change formula, because they're both given to us in the problem. Okay, so that was nice. There's the rate of change. It's 3x squared minus 10x plus 8. There's the second rate of change, which is 6x minus 10. So your 4.4 homework that you're working on for tonight is all about second rate of change functions. And now we're just answering some questions here about the original function. Remember, we're asking questions about the original function, but we have to use these rate of change functions to help us answer these questions. First, what's the y-intercept? That's so easy. That's not even a calculus question. We find the y-intercept just by plugging 0 in for x, right, in the original function. So when you plug 0 in for x into this function, all those terms are going to just disappear, right? So you're going to end up with just 0. So you have a nice simple y-intercept there. It's 0. For the x-intercepts, that's trickier. To find the x-intercepts now, where does this function cross the x-axis? You need to set the formula to 0. So we have to take 0 is equal to x cubed minus 5x squared plus 8x. and try to solve that equation. That's a tough equation to solve, let me tell you. You can start by factoring an x out of all of these terms, so you get x times x squared minus 5x plus 8. And now you can set both of these terms to 0, because see, here you have a product, and the only way this product is going to be 0 is if either x is 0 or x squared minus 5x plus 8 is 0. So you can set x equals 0, and that gives you one solution to the equation. So one of your x-intercepts is 0, or it could be that x squared minus 5x plus 8 equals 0. And now you're trying to solve this equation to see if you have any more x-intercepts. Well, normally you would try to solve that equation by factoring, but that expression does not factor, so you're stuck with using the quadratic formula. But you can use the quadratic formula, but it turns out that when you use the quadratic formula, here's what you get after you apply the quadratic formula. So I'm not going to go through the whole process of plugging these coefficients into the quadratic formula. You might want to put your quadratic formula on your index card, by the way, for Wednesday. But here's what you end up getting, okay, when you plug A, B, and C into the quadratic formula and simplify. You end up getting 5 plus or minus the square root of minus 7 over 2. And you know square root of minus 7 is not a real number. That is not a real number, right? Okay, square root of minus 7 is an imaginary number. And so that means that you don't have any real number solutions to this equation. In other words, there aren't any more x-intercepts, okay? The only x-intercept is 0. If you make a graph of this curve, you'll see it only crosses the x-axis at 0. It gets really close to the x-axis again, but that's the only places that it actually crosses the x-axis, okay? So no more x-intercepts other than 0, okay? All right, well, okay, so there it is. All right. Now, however, let's see if we can figure out where the possible turning points are. So maybe even though it doesn't have any more x-intercepts other than 0, maybe it has some turning points. So maybe it has some wiggles on the curve, right? And let's see if we can find out where the location of those turning points are. Okay? And how do you find location of turning points? So here's another thing to write down on the index card. What do you do to find the location of the turning points? You aren't jumping up and shouting the answer to me, so that worries me a little bit. What do you do? Set the first derivative 0. Yeah, that's what I wanted to hear there. Set the first derivative to 0. Okay? Set the first derivative to 0. Okay? So this brings us, there's the first derivative, though, so we didn't have to find the first derivative. That was given to us, so that was nice. So we just set that equal to 0, and now we try to solve that equation, okay? And again, that's a quadratic equation, so you would start by trying to solve it by factoring. But if you can't factor, you can always use the quadratic formula. And maybe it turns out that this equation doesn't have any solutions. That's a distinct possibility, in which case you won't have any turning points, okay? You don't have to have turning points on curves. Just because you have a curve doesn't mean you have turning points. But this actually does factor. So now, it's easy to give up on trying to solve this one by factoring, because the factoring here is not obvious, but it does factor. That's how it factors. It factors as 3x minus 4 times x minus 2. And so that means that either 3x minus 4 equals 0 or x minus 2 equals 0. So you can solve these two equations. So those are real easy to solve. One solution is 4/3, which is about, in decimal terms, that's about 1.33, right? Okay? And the other solution is 2. Okay? So you have a turning point, a possible turning point. Maybe it doesn't turn out to actually be a turning point. We'd have to look at the graph to actually verify this. But we have a possible turning point at x equal 4/3, and another possible turning point at x equal 2. Now, however, you cannot stop here. You will not get full credit if you stop right there, okay? Because this says this question says it wants the coordinates of the turning points. So that means both the x coordinate, which are going to be these two numbers, and the y coordinate. It also wants the y coordinate. So to find the y coordinate, you're going to have to take these two values and plug them back into your original formula, right? Okay, not into the first derivative. Don't plug those into the first derivative, because if you plug these numbers into the first derivative, you're going to get 0, okay? No, take those two x coordinates and plug them back in to the original formula, okay? So that takes a little bit of arithmetic, because you got to plug the 4/3 or the 1.33 in for x here and do the arithmetic, and it comes out to be, I did it yesterday, so it comes out to be about 4.15 approximately, okay? So you have one of your possible turning points is at 1.43 and 4.15, okay? That's the x coordinate, that's the y coordinate. And then the second possible turning point is a little bit easier. You just have to plug 2 into your formula, okay? So in other words, calculate h of 2, plug 2 in here for x, and that works out to be 4, if I did the arithmetic right. So there's your second possible turning point. Is that really, are these really turning points? I'm not sure. I'd have to look at the graph to verify if these really are turning points, but at least those are possible turning points. So it's possible that I've got some peaks or valleys on my graph at these 2 points. Right, so y'all got that? Because that will definitely be on test number 3. Okay, question like this one will definitely be on test number 3. What about inflection points? How do you find the inflection points or possible inflection points? What? The second derivative 0, right? It's the same story. Over and over and over again in math, you have this same problem present itself. You find the x-intercepts by setting the formula to 0. You find the turning points by finding the first, setting the first derivative to 0. You find the inflection points by finding the second, setting the second derivative to 0. See, okay, there's a nice clear pattern there that makes it easy to remember how to find intercepts and turning points and inflection points. So you take the second derivative, which we were already given there, right, and set that to 0, and that's a real easy equation to solve. We just get 6x is equal to 10, and that works out to be x is 10 divided by 6, which is 5/3. So there's the x coordinate of our possible inflection point. 5/3 is approximately 1.67. So you find now the y coordinate of that possible inflection point by plugging the 1.67 back into the original formula. Make sure you go back into the original formula, right? And that works out to be, according to my arithmetic, 4.07. So there is our possible inflection point where the concavity would change, right? Where it would change from concave up to concave down or vice versa, right there at 1.67 and 4.07. What now? I want the point, so I want... The decimal is fine. It gets a little bit clumsy to take 5/3 and plug it into this formula. It's easier to do it with, you'll need a calculator, so it's easier to do it with decimals. Okay? All right? Mm-hmm. Which one? This one? Yeah, that's always the way you find the y-intercept of any function. You set x to 0. Okay? Yeah, okay. To find the y-intercept, always plug 0 in for x. That's just a rule. Okay? So when you plug 0 in for x, all those terms disappear and you just end up with 0. So the y-intercept there is also 0. Okay? All right, let's stop there. Okay, and I won't go on and do this problem. We've done, oh gosh, 10 problems like this now, okay? This is where we're trying to maximize profit, okay? And so I've got the review answer set up, so you can take a look there at how to maximize profit, okay? Definitely be a problem like this one, similar to this one on the test number 3, okay? All right. I want to show you now, we've got just enough time, okay? And I want to show you now a few examples of how you can find the area under a curve. So in other words, how you can do integration precisely, exactly, without having to just get an estimate, all right? So without having to use rectangles to get an estimate or some other way of getting an estimate, okay? And it turns out that in order to do this, there's a surprising relationship and an important relationship between integration, so that process of finding the area under a curve, and, who would have thought it, differentiation, okay? And I'm going to show you that relationship now. So actually, these two problems that we've studied in this class, differentiation, finding rates of change, and integration, finding areas under curves, although we spend a lot less time on that. That second problem of integration, finding the area under a curve, those two problems turn out to be closely related to each other, okay? And they're related by what is called, so we've hit the high point of the course here on the last day, the fundamental theorem of calculus, okay? So this is considered the most important theorem in the whole, or fact in the whole study of calculus. All right, so let me show you what the fundamental theorem says, okay? And then, of course, when you see it written down, it's a little bit abstract, but when you start seeing some examples, it becomes clear how to use the fundamental theorem. All right, so suppose we have a function, it's got to be a continuous function, all right, and we're trying to integrate that function. So we're trying to find the area under the curve, right, under the graph of that function, right, from A to B along the x-axis, right? So we're trying to do integration with this function, okay, finding the area under the graph down to the x-axis of that particular function, okay? So what the fundamental theorem says is this. Suppose you can find a second function. I'm going to call it a capital F, okay? Suppose you can find a second function, capital F, such that when you take the rate of change of capital F, okay, you get the function that you started with, lowercase f. All right? So be very careful here that you distinguish between uppercase f and lowercase f. All right? So here's the function that we're trying to find, that we're trying to integrate. All right? This is lowercase f. Okay? But suppose we can find a second function that I'm calling capital F, so that when you take the rate of change of capital F, you get lowercase f. All right? Such a function, by the way, capital F, is called an antiderivative. Okay, an antiderivative. So not a derivative, but an antiderivative. So you want to find another function so that when you differentiate it, you get lowercase f. Okay? So suppose you can find such a function. Then it turns out that the value of this integral is easy to calculate. Amazingly, it turns out that the value of this integral, this area under this curve, is very easy to calculate. All you have to do is take the antiderivative function, plug b into it, and subtract off what you get when you plug a into the antiderivative function. Isn't that easy? Okay? So, you're shaking your head there, all right? I bet you will see it turns out to be, in many cases, surprisingly easy, all right? But now keep in mind what this function capital F is. Capital F is not the derivative of lowercase f, all right? I didn't write little f prime here, okay? It's the antiderivative. It's a function whose rate of change is lowercase f, okay? It's a function whose rate of change is lowercase f. So you have to think about that, all right? You have to think about finding this so-called antiderivative function. But once you've found it, then this integral turns out to be very easy to evaluate, okay? Because all you do is just do a little bit of arithmetic with the antiderivative function, all right? Okay, all right, so that all seems kind of obscure, right, until we start looking at some examples. So that's what we're going to do now. Let's do several examples here of applying this so-called fundamental theorem of calculus, and we'll be able to calculate these definite integrals really easily. Okay? All right, so let's start with a very simple example. Okay? This is about as easy an example we can start with. Okay? Let's see if we can find this definite integral. So remember, what does this mean? This means the area under the curve, 4 minus x, from 0 on the x-axis to 6 on the x-axis. I picked this example on purpose. Let me show you why. Because, for one thing, it's easy because that formula 4 minus x is really easy, right? Okay, so I picked that one because it's easy. But let me show you another reason why I picked it. This also happens to be on the sample test. So we're going to a test here. See if I can find. There it is. Okay. That curve on the sample test, all right, which was problem 9. Oh, I said wrong here a moment ago. It's problems 10 and 11. Problems 10 and 11 on the sample test. Those are the ones we're delaying to the final exam. So these two problems, 10 and 11, will not be on test number 3. But problems like those will not be on test number 3. They'll be on the final exam. Okay, but a problem like this could be on test number 3. Okay, this is an integration problem, but it's a really easy integration problem, right? Because this curve is very simple, and you can calculate this one just using your knowledge of geometry, right? Okay. Now, I didn't tell you in the sample test what the formula for this function f is, but I'm telling you now, it's 4 minus x. Okay, so this function is 4 minus x. All right. Okay, let's see if we can calculate this integral using, so let's see if we can calculate this area just using geometry, and then we'll test the fundamental theorem of calculus and see if we get the same value. Okay, if we don't get the same value, then we're in trouble, right? So something has gone wrong. All right, so let's do this problem from the sample test first. Okay, all right, so this should be a pretty easy area to calculate, right? Because it just involves 2 triangles, correct? Right? You've got this triangle here that's above the x-axis that I've got colored green, and you've got this triangle that's below the x-axis that I've got colored red. And the reason I've got this one green and this one red is, remember, this area is going to come out positive, right? Because that's above the x-axis. And what about this area? It's going to come out what? Negative, because it's below the x-axis, all right? Well, all right, so let's see if we can calculate the area of this triangle. So remember, what's the a formula for the area of a triangle? It is, so you need to write this on your index card for Wednesday, right? It's 1/2 the base times the height, right? Okay, so for this green triangle, what's the base? So what's this length here on the x-axis? What? Yeah, that's 4. So we get 1/2 times 4 times, and the height is easy to see too, because that's going to be what? Just what? That's also 4. So we get 1/2 4 times 4. Oh, that's so easy. That's 8. Okay. So this green area is 8, right? All right. Now let's see what the red area is. Well, it's still a triangle, right? So we're going to use the same triangle area formula. So we get 1/2 times the base. But what's the base here? 2, right? Because we're going from 4 to 6, right? So the base there is 2. And what's the height? It's also 2, right? Okay. So that's also 2. So you end up there with just 2. Okay. But remember now, this is below the x-axis, right? So you're going to interpret this area as negative. So make sure that you put a minus sign here, right? Okay? Because you're going to get a negative area, not a positive area. Yeah?
Before I look at your answer sheet,
Mm-hmm.
it says I solve Your answer for 2 for the red one and that one it was positive 2 in your answer sheet.
Yeah, but notice what I did with it. When I calculated the total area here, you add these two areas together, right? So you end up getting what? 8 minus 2. So altogether you get what? 6, right? Okay. So I just wrote it slightly different here than I wrote it on the answer sheet. But I come up with the same result, right, which is 6, correct? Okay, yeah, right, okay. So this integral is 6, okay? That positive area 8 plus the negative area minus 2 gives you a total there of 6, okay? All right, so that's really easy. Just using geometry, let's see now if we can do this with the fundamental theorem, okay? So what does the fundamental theorem require me to do, all right? I've got to find a function, so I'm going to call it capital F. I've got to find a function, but you want that function so that when you calculate its rate of change, you get 4 minus x, okay? So we've got to sort of think backwards here. What function, when I find its rate of change, would give me 4 minus x? So we're going to take our kind of derivative rules and we're going to apply them backwards. All right? So let's take it one term at a time. Start with the 4. So what function would give you 4 as its derivative? 4x, right? Okay? Isn't that right? Because if you find the rate of change of 4x, what do you get? 4, sure, right, okay? You're going to get 4, correct? All right, so there's the start of my antiderivative, okay? Now, this x is a little bit harder to think about, okay? But let me show you how to do it, all right? So easy. You're just going to reverse your power rule. You're going to reverse the power rule. So remember, the power rule says when you're finding a rate of change, what do you do with an exponent? You subtract 1 from it, correct? Okay, and you bring the exponent down as a factor. Well, we're just going to do the opposite. Instead of subtracting 1 from the exponent, we're going to add 1 to the exponent. So for that term x, I'm going to add 1 to its exponent, and that's going to give me 1 plus 1. Okay, and I'm going to also, instead of multiply by the exponent, I'm going to divide by that new exponent 2, okay? I claim that is the right expression whose derivative is going to be x. All right, let's check this now, okay? So first let me simplify it. So I have 4x minus, what is this, x squared over 2? Okay, so let's figure out what the rate of change of this function capital F is, okay? It's supposed to come out to be 4 minus x. If it doesn't, then I got to go back to the drawing board. But let's see if it will come out as 4 minus x, okay? I promise you it will, I think. All right, let's hope for the best. All right, so what's the rate of change of 4x? 4. Okay, well, that part was easy, right? Okay, so now I get 4. Now, what's the rate of change of x squared over 2? So what do you do to find the rate of change of x squared over 2? You bring the what?
2.
You bring the 2 down, right? Okay, so you get 2 times x to the 2 minus 1, correct? And then don't forget you've got that 2 there. So, right? You've got this 2 here, right, in the denominator. What happens to the 2's, though? They cancel very nicely out. And what do you end up with here? Perfect, right, okay? Just 4 minus x, okay? So see, that was easier than we thought it was, okay? There is the so-called antiderivative function, okay? 4x minus x squared over 2. Now, we haven't applied the antiderivative function yet. I just found it, okay? I want to caution you about one thing about antiderivatives. 4 minus x is going to have a lot of antiderivatives. There are actually a lot of possible functions whose derivative is 4 minus x. Because all you have to do here to get another antiderivative is add on any constant you want. You could add on any constant you want and to this function and get a new function whose derivative is still 4 minus x. See, I can add a 1 on here if I wanted to, right? Because when you find the rate of change here, well, the rate of change of 4x is 4. The rate of change of x squared over 2 is x. But, of course, what's the rate of change of 1? 0. So you would still get the same formula here, 4 minus x. So there are actually lots of antiderivatives you could try here. But the easiest one is just don't add a constant on. Just keep a 0 at the end. Okay? All right, so let's use that one, 4x minus x squared over 2. Okay, so now what does the fundamental theorem say you're going to do with the 4x minus x squared over 2 to evaluate this integral, this definite integral? So here's the second step of the fundamental theorem. It says, oh, I know what the value of this integral is. I'm going to plug 6 in to my antiderivative, and I'm going to plug 0 in to my antiderivative. And then I'm just going to take the difference of those two values, and that will be my area. Y'all believe that's true? I'm kind of doubtful now. Okay, so just plug 6 in to the antiderivative and plug 0 into the antiderivative and take the difference of the two, and that gives you the area. All right, let's see what comes out here out of this. All right, so let's take 6 and plug it in here. So I get 4 times 6 minus 6 squared over 2, right? Okay. That's plugging the 6 in, and now you have to also plug in the 0, okay? So that would be 4 times 0 minus 0 squared over 2, right? So I plug 6 in, and then I plug 0 into this formula. All right, let's see what we get when we plug the 6 in. Well, what's 4 times 6? That's 24 minus, what's 6 squared over 2? That's 36 over 2, which is what? 18 minus, and of course, what are you going to have in the parentheses here? 0. So you end up with 24 minus 18 minus 0, and what does that work out to be? 6. Exactly what we thought it was supposed to be, right? Okay, we get 6, which we know to be the correct area. Wow. Okay. Well, that's not just a coincidence here, okay? The fundamental theorem is proven to be true, so you know that when you're trying to evaluate a definite integral, if you can find an antiderivative, that's the tricky part. If you can find the antiderivative, then it's going to be easy to evaluate that integral. It's going to be easy to find that area, okay? So that's really a stupendous fact, all right? And a very exciting fact when mathematicians first discovered this, okay? Because it greatly simplifies this problem of determining these areas under curves. All right, let's try another one. So I got another easy one, and then we'll try a little bit harder one, okay? So I don't know what the answer to this one is supposed to come out to be, so let's make sure we don't make any arithmetic mistakes. All right, so I want to find the integral from minus 2 to 4, okay, of 3x minus 6. So the area under this curve, 3x minus 6, from minus 2 to 4. I don't have a picture of that drawn, okay? No reason to draw a picture of that, but I can visualize that in my mind, right? Okay? I can visualize that area. Okay, so let's see if we can find that area using the fundamental theorem. So the first thing you've got to do is find the antiderivative. So in all these problems and on your test, I'm going to call that antiderivative capital F. Okay, so let's see if we can find capital F. All right, and in this case, here's what you're going to do. All right, you're going to just go term by term and try to find the antiderivative of each term. And again, you can use that reverse power rule, okay? You can use that reverse power rule. So what does the reverse power rule say? It says, oh, this is really easy to find the antiderivative of 3x, okay? all I have to do is add 1 to the exponent instead of subtracting 1, because if you're finding the derivative, you subtract 1. So I'm going to add 1 to the exponent. This exponent is 1. And then what am I going to divide by? 2, right. Divide by your new exponent. Okay? So I claim that 3x squared over 2 is the antiderivative of 3x. We'll check that in just a second. Okay? What about the antiderivative of 6? That's 6x. That one's so simple, right? Okay? We know that's got to be 6x. So we think the antiderivative here is 3x squared over 2 plus 6x. And again, you can add on, if you wanted to, you could add on any constant, any number that you like at the end, and you will still have an antiderivative. But there's no sense to add on a constant because this is an antiderivative already. Okay? All right, so now let's check to make sure that that really is the correct antiderivative. So let's find its rate of change and see if we get 3x plus 6. So how would we take the rate of change of 3x squared over 2 plus 6x? Well, you would bring the 2 down, right? Times 3x to the first power over 2, right? Subtract 1 from the x squared. And then what's the rate of change of 6x? 6. And of course, these 2's divide out, so you end up with just 3x plus 6. So we found the correct antiderivative, right? We find its rate of change, and we get what we had here behind the integral. So now to evaluate this integral, that's so simple. All I have to do is take the limits of integration and plug them into my antiderivative formula. Okay? So in other words, you're going to calculate capital F of 4 and subtract off capital F of minus 2. The what now? The 3 doesn't have anything to do. I don't know what you're asking me there. When I was finding the rate of change, I did bring the 2 down. Okay? You could think of multiplying it by the 3. That would give you 6. But ultimately, when you divide by 2, you're going to get back to 3 again, right? Okay? Yeah. You can do it either way. Yeah. Okay. All right, so now you've got to help me here. What is f of 4? Okay? All right, what is f of 4? So let's go off to the side here and calculate f of 4. Here's my formula for f, right? Remember, this is not the formula for capital F. This is the formula for capital F, right? So we're going to get what? 3 times 4 squared over 2 plus 6 times 4. So what does that work out to be? 3 times 16 is that 48? Divided by 2 is 24 plus another 24, 6 times 4. So I end up there with 48. So capital F of 4 is 48. What about capital F of minus 2? Be very careful here because you've got a lot of exponents. So you have 3 times a minus 2 squared over 2 plus 6 times a negative 2, right? So that's 3 times a 4, positive 4, divided by 2. And then 6 times a negative 2 is a minus 12. So I end up here with 12 over 2, which is 6 minus 12. So that looks like minus 6. Now, here's where you're going to want to make a sign mistake. F of negative 2 is minus 6, right? F of capital F of 4 is 48. Capital F of minus 2 is minus 6. Remember, here you're subtracting, though. So you're going to get 48 minus a minus 6. So watch out for that, right? This minus is part of the theorem. This second minus came about because capital F of minus 2 just turned out to be minus 6. So you end up with a double negative there. So altogether, you get 54. So apparently, if we drew a picture of this curve, right, okay, which is a straight line, and looked at the area under that curve from -2 to 4, it would turn out to be rather a large value there. It would be 54. That's the way it works, though. Okay? So if you can find these antiderivatives, which is sometimes easier said than done, okay? But if you can find those antiderivatives, then evaluating these definite integrals turns out to be really just a piece of cake, right? It's just arithmetic, all right? So you don't have to do all this rectangular approximation business. You can just do it with arithmetic, okay? What a great relief to mathematicians when they discovered this, okay? Because it's very hard to do those rectangular approximations, especially when you don't have a calculator, you see, okay? So this is a great time-saving device when it was initially discovered, okay? Someone had their hand raised. Let's try another one. Got time for at least one more here. All right, so again, I'm jumping the gun, okay? So again, to evaluate this definite integral, I've got to find my capital F, my antiderivative. But this is another case now where I can just use the power rule, okay? So another simple case where I can just use the reverse power rule, I should say, okay? All right, so let's see what this antiderivative is going to look like. So you're going to take 3 times x to what power? 2 plus 1. Yeah, 2 plus 1, right? So 3x cubed, and then divide that by 3. See, that power always comes as a into exponent here, all right? Plus, and then for this term, you would have 2x squared, add 1 to the exponent 1, and then divide by that exponent. So this one works out really nicely because the coefficients divide out, right? So you end up with just x cubed plus x squared as your antiderivative. Cool, okay.
So you can just like put x cubed instead of going through all the process?
Well, these 3's divide out, right?
Yeah.
Okay, so yeah, so you can just put x cubed there. All right, and these 2 divide out, so you can just put x squared. Let's see, is that correct? I think that's pretty easy to check that that's correct, right? What's the rate of change of x cubed? Oh, that's got to be 3x squared, right? And what's the rate of change of x squared? Oh, that's got to be 2x, right? So, yeah. So we know we got the right antiderivative there. And now to evaluate the integral, let me rewrite it here. So I have integral from 0 to 2 of 3x squared plus 2x. I just take capital F of 2 and subtract off capital F of 0. So make sure you subtract off capital F of the lower limit there, right? Well, let's see. What is capital F of 2? That's going to be 2 cubed plus 2 squared, right? And we're subtracting off from that 0 cubed plus 0 squared. So I'm not subtracting off very much, right? I'm only subtracting off 0. Okay, so my area turns out to be just 2 cubed plus 2 squared. So that's 8 plus 4, which is 12. Perfect. All right, let's check this one, because I actually, let me see. There is that curve, 3x. Did I type that in right? 3x squared plus 2x? Yeah, okay. And let's check this one by actually summing up a bunch of rectangles and see what we get as an approximation. So it's got to come out to be approximately 12, right? Okay, so what's my lower limit? Where do I start at in that problem? 0, but where did I go up to? I didn't go up to 6. I went up to what, 2? Right here. So in other words, I'm looking for this area beneath the curve from 0 over to 2. So this little piece right here, which is almost but not quite a triangle, right? Okay. So let me change this to 2. And now we're going to do this approximately by filling it up with rectangles. Here I have 6 rectangles, but let's not be shy about the number of rectangles there. Let's put in, let's try 60,000. How's that? Okay. All right. So that should give me a very close approximation, correct? So in other words, I'm thinking of I can't draw it here on the screen, but I'm thinking of drawing a bunch of little rectangles, right? Filling up this area with a bunch of little rectangles, starting at the x-axis and going up to the curve, and then adding up the area of all those little rectangles. That would give me 60,000 numbers to add up, so that would take me a little while if I were doing that by hand. But fortunately, Desmos is going to do that for me, and what does it tell me the sum is? Okay, 11.9997, okay? And if you try 600,000, so you can see you're just going to get closer and closer there. Let's try 6. I wonder if I put 6. I've never tried 6 million on there. Okay. Every time you add more rectangles, notice that your approximation is just getting closer and closer and closer to what? Obviously, what? 12, right, okay, which we already know to be the exact value, okay, from the fundamental theorem, okay? So with a tool like Desmos, we could approximate the area, right, very nicely by using rectangles, but without a tool like Desmos, right, we would be really hard-pressed to do that by hand. That's where the fundamental theorem is really very helpful, okay? Let's do one more now, really, really fast, okay? All right, so this problem number 4, you guys tell me, what is the antiderivative, okay? What is the antiderivative of 1 minus x squared, all right? So, and again, it's just a matter of reverse engineering that antiderivative. Doesn't work out quite as nicely as example number 3, but it's not too bad. Okay, so what did y'all get for the antiderivative there of 1 minus x squared? What's the antiderivative of 1? Yeah, that's easy. That's x. And what's the antiderivative of x squared? X cubed divided by what? 3, right. Perfect. Okay. Yeah. Okay. And you can easily check that just by finding the rate of change of capital F here, the rate of change of x is 1, and the rate of change of that second term, you're going to bring the 3 down and subtract 1 from the exponent and then divide by 3, so the 3's will cancel out, so indeed you'll get 1 minus x squared. Okay, so that's the antiderivative, x minus x cubed over 3, and then to evaluate the actual integral, you have to take f of the upper limit of integration, so capital F of 1, and subtract off capital F of minus 1. All right? Be sure you're subtracting off the capital F of minus 1. So tell me what y'all get there. This one's going to involve a fraction, I think. Okay? So you have to do a little bit of fractional arithmetic. Little bit. Okay? So plug 1 in there, and then plug minus 1 in there, and take the difference and see what you get. All right, hang on a second there. All right. So this is what your homework, the second integration homework is going to entail, okay, is finding some of these antiderivatives and then applying them to evaluate some of these definite integrals. So that's like the last 2 problems on the test number 3 review, okay? And again, that will be on the final exam. Now, some of the problems in the homework are a little bit more challenging, Okay? Finding the antiderivatives are a little bit more challenging, so you may have to think about some of those on the homeworks. Okay? All right, so what did we get there? What is capital F of 1? Capital F of 1, that's going to be what? 1 minus 1 cubed over 3. So is that 1 minus 1/3, which is 2/3? Is that right? All right, so you're taking 2/3 and you're subtracting off of that f of -1. So that would be -1. Wow, this one's hard. -1 minus a -1 cubed over 3. So does that come out to be -2/3? I think so. All right. And so altogether here, where am I looking at? I've got 2/3 minus a -2/3. See, you're subtracting off because you've got a subtraction as part of the formula. And then this f of -1 is -2/3. So you end up with -2 plus 2/3. 2/3 plus 2/3, which is +4/3. So it looks like the area under this curve from -1 to 1 is exactly +4/3. Okay. All right, so we're out of time. Does everyone know now what they're doing between now and next time? You've got to fill out your course evaluation if you want those $5, your class activity, and finish your homeworks. Integration Part 1. Go to the test review with John right now, okay? Do your test review, your number 3 test review before Wednesday, okay? So you can make a good grade on that test.